Welcome back. In our last classes, we have seen continuity and derivative of a function. And today, before moving any further, let's see a connection between the continuity and differentiability of a function. So, what is differentiability? A function f is said to be differentiable if it has a derivative. So a function f is said to be differentiable if we can find a derivative for that function, or if the function has a derivative. What do we mean by saying that a function has a derivative? We have seen an expression for derivative like f of x equal to f of x plus delta x minus f of x divided by delta x. Right. If this expression makes meaningful sense when delta x is very small or delta x goes nearly zero. In such a limiting case, if this expression exists or this expression has a valid meaning, then we may say that the function has a derivative and the function f is differentiable. Right. So, is there any connection with differentiability and continuity? Let's just state it and leave. If a function needs to be differentiable, it has to be continuous. So, a function is differentiable implies it is continuous. So, a non-continuous or a discontinuous function cannot be differentiable. And if a function is differentiable, we have one more inference from that, is the graph of the function will have unique tangents everywhere. The graph of the function will have unique tangents everywhere. See, we have seen the tangent line to the graph of a function. We know how to evaluate the slope. We have seen that the slope of the tangent and derivative are almost same. And if a function is differentiable, the graph of such a differentiable function will have unique tangents everywhere. Right. So, this is how differentiability is directly connected to continuity and tangents. Now, let's see a practical application of this in economics. Before moving to the precise application question, let's get familiarized to a few terms. So, what is marginal cost? So, those who are from economics might be familiar with this word, but those who doesn't have any background with economics may find this as a new thing. And marginal cost is defined as the rate or the change in total cost associated with a small change in the quantity produced. Or, in other words, suppose we have a production unit and the unit produces X units and the cost of producing X unit is C of X. Right. Then the marginal cost is the rate of change of C of X with respect to X or simply C dash of X. See, we have seen that the rate of change is nothing but the derivative. Okay, so to be a little more mathematical, marginal cost is the derivative of the cost function. Marginal cost is the derivative of the cost function. Similarly, we have marginal revenue. Right, which will be obviously, if R of X is the revenue function, then derivative of revenue function will give us the marginal revenue as a function. Right. Now let's move to the practical question. So I won't write the whole question, but the key points. Suppose we have a firm, a production unit, and the revenue function R of X is given as R of X equal to 50x minus 2x square. 50x minus 2x square. Can we find the marginal revenue function? Find the marginal revenue function. So we need to find the derivative r dash of x. We know how to find the derivative of this function. We have certain techniques, but for now we will use the formal definition of derivative, like using that limit thing. Okay, so r dash of x, we have defined r dash of x as the limiting case of say r of x plus delta x minus r of x divided by delta x as delta x goes to 0. We can restructure this or instead of just writing delta x goes to 0 here, this is actually a limiting case. We can rewrite this as limit delta x goes to 0 r of x plus delta x minus r of x divided by delta x. Right? These are exactly the same. If you don't write limit delta x tends to 0 here, you will have to repeatedly saying that delta x is being approximated to 0 or it is going infinitesimally smaller. Right? Or else you just fix it delta x, limit delta x tends to 0 here. Let's evaluate this. So limit delta x goes to 0. What is r of x? R of x is 50x minus 2x square. So what is r of x plus delta x? 50 into x plus delta x, don't forget this bracket, minus 2 into x plus delta x whole square minus what is r of x? Again a bracket for this minus 50x minus 2x square whole divided by delta x. So let me clear what we have written here. So this is equal to limit delta x goes to 0. If you try to open this up, 50x plus 50 delta x. Remember, this is not delta into x, it's as a single term delta x, which just means it's a small quantity in x or a small increment in x. Alright, so minus 2 into, what is this? X plus delta x whole square, so it's of the form a plus b whole square. So let's expand it, x square plus 2x delta x plus delta x square. Let me repeat, this is not delta into x square, it's delta x whole square. Minus, let's open the bracket here, minus 50x minus into this negative will be positive plus 2x squared. Right. So this 50x and this 50x can be cancelled out. Oh, we have a delta x to divide whole with. Right. So this is equal to limit delta x goes to 0. 50 delta x minus, let's open this bracket up, 2x square minus 4x delta x minus 2 delta x squared plus 2x square divided by delta x. So this is equal to limit delta x goes to 0. See, we can cancel out this 2x square and this negative 2x square, and see we have a delta x in all other terms left. Right, this is delta x square means delta x into delta x. So we can take out a delta x into 50 minus these two terms are, they are gone, minus 4x minus 2 delta x. This was 2 into delta x and the delta x is taken out, divided by delta x. And now we can cancel these 2 delta x's out, which will be limit delta x goes to 0, 50 minus 4x minus 2 delta x, and this is of a polynomial form, so we can directly substitute delta x equal to 0 in the expression to find the limit. So this will be 50 minus 4x minus 2 into 0, which will be 0. Doesn't make any sense to write over there. So this is the answer, or the revenue, or the marginal revenue. The marginal revenue as a function of x is 50 minus 4x. Right. So this is one among the wide applications of derivatives in economics, and we have similar applications in biology or every other field of social sciences and pure sciences. So remember, for now, derivatives has a wide application, wide range of applications, and this is actually just a glimpse to that. Okay, so that's all about this chapter, and in our next chapter we will be discussing extensively on the techniques of differentiation. So we have seen what is a derivative, what do we mean by derivative, and we have got an expression or a formula or a formal definition to evaluate the derivative of a function. And in the next chapter we will be finding a few more techniques and a few more rules or properties or theories of derivatives and differentiation, which can indeed make our work easier, or will be a much more shortcuts to finding the derivative of a function. So now let's go to the next chapter. It's all about differentiation. So what is differentiation? Differentiation is the process of finding derivative of a function. Suppose we have a function f of x, and we are trying to find the derivative f dash of x, which was how we denoted it. Before forwarding any further, let's discuss about a few notations of the derivatives. Suppose we have a function represented as y equal to f of x. Then there are certain ways in which the derivative of these functions, what function can be denoted. F dash x is a way. F dash x can be, this is a way in which the derivative is denoted, and y dash is another notation. This can be dy by dx as well. You might be familiar with these things, and maybe df by dx, or just d by dx of f of x. This is also fine. Or even very rarely, but this is also fine, dx of f of x. This expression means derivative of f of x with respect to x. So how many do we have here? If y equal to f of x, f dash x, y dash, or simply f dash is also fine. Dy by dx, df by dx, dy dx of f of x, dx of fx, or dx of f of x. So we have 1, 2, 3, 4, 5, 6 different notations, and there can be many more. So all these denote the same concept of derivative. Right. Now let's see a few rules of differentiation. Rules. Let's go one by one. Suppose we have a function, a constant function, f of x equal to k. We have a constant function, f of x equal to k. Then the derivative f dash of k, so f dash of x is defined as 0. Right. So the derivative of a constant function is 0. Why does this happen? See, how did we define the derivative? As the rate of change. See, if this is a constant function, it is not going to change anywhere. So the change is 0, and thus the rate of change is 0, and for that reason the derivative of a constant function happens to be 0. Right. This rule, claiming that the constant function has a 0 derivative, is called the constant function rule. Constant function rule. You may write the notes yourself, and this happens for any constant, say if f of x equal to some 2 or f of x equal to some 2 lakh, whatever the constant may be, the derivative will be 0. The derivative will be 0. So that's the constant function rule. The next is linear function rule. Linear function rule. We have seen a linear function. So a linear function f of x will look like some ax plus b. Right, where a and b are constants. In such a case, the derivative of f is defined as f dash equal to the coefficient of x, that is a. So the derivative of a linear function is a constant. Okay, so and that constant is the coefficient of x, and if you try to graph this as a line in a plot or a coordinate system, this a happens to be its slope. Okay, so we remember that we have defined derivative as slope as well. Right, so this coincides with our former definition of slope and derivative. Right, so let's see an example. If f of x equal to some 7x plus 29, some 7x plus 29, then derivative of f dash of x is 7. Whatever this constant may be and whatever the value here may be, it doesn't gonna change anything. The derivative of a linear function will be exactly the coefficient of x, or the slope of the line which is represented by that linear function. Okay, so that's the linear function rule. The next rule is power function rule. Suppose we have a function f of x given as f of x equal to x raised to n. F of x equal to x raised to the power n. Then the derivative of f dash of x is defined as, this is x, n into x raised to n minus 1. Okay, see, this is true for any real number n. So the derivative of f of x equal to x raised to n is denoted as f dash of x and is defined as n into x raised to n minus 1. So let's directly go to an example. This is pretty simple. Suppose we have f of x equal to x raised to 100. Right. Then f dash of x is 100 into x raised to 100 minus 1, which is 99. Okay. So this is the power function rule. The rule for constant times a function. Constant times a function. Suppose we have a differentiable function g of x. So g of x is a differentiable function, and we define a new function f of x using g of x as f of x equal to a constant k times g of x. Right, a constant k into g of x. Then the derivative f dash of x is k into g dash of x. Okay, the derivative of a constant times a function is constant times the derivative of the function. Right, or simply we can take the constant out of differentiation. We can take the constant out of differentiation. Okay, so do we need any example for this? Let's see. Say f of x equal to 6x raised to 4. Right, so here we have two functions or a function x raised to 4 and a constant 6. So if you need to find the derivative f dash of x, take the constant out, 6, and derivative of x raised to 4. This is a power function, and the derivative of x raised to n was defined as n into x raised to n minus 1. So the derivative for x raised to 4 will be 6 into 4 x raised to 4 minus 1, which is 3. So this will be 4 into 6 is 24x cube. Right. So this is how we make use of this constant times a function rule in evaluating the derivative of functions. Right. So the next is for rule for sums and difference. is just an obvious thing again. Suppose we have a function f of x which can be expressed as the sum or the difference of two other differentiable functions, say f and g, or g and h. Say g of x plus or minus h of x. So f of x is g of x plus h of x or g of x minus h of x, whatever the rule is same for both sum and difference. Right. Then the derivative f dash of x is simply g dash of x plus or minus h dash of x. Or inverse, the derivative of the sum is the sum of individual derivatives and the derivative of the difference is the difference of individual derivatives. Right. So let's see an example if you want to. Let f of x equal to 8x raised to 4 plus 5x cubed. 5x cubed. Right. Then f dash of x is, as per our previous, the sum rule for sum and differences, we can individually differentiate both of them and sum or them and add them. So what is the derivative of 8 into x raised to 4? 8 can be taken out. X raised to 4 will be having the derivative 4 into x cube. So 8 into 4, 32. So 32x cube plus 5 can be taken outside. 5 into 3 into x raised to 3 minus 1, which is 2. So it will be 15x square. Right. So this is how we differentiate the functions having a plus inside. We can differentiate term by term. Right. The same can be applied for differences as well. Does not make any change. So that's the rule for sum and difference. And then comes the product rule. This is way more important. Suppose we have a function f of x which can be expressed as the product of two differentiable functions as f of x into g of x. Unlike addition and subtraction, we cannot simply differentiate both of them and multiply them. Instead, we have a formula to use. The derivative of f dash x is defined as, listen, f of x into g dash of x plus g of x into f dash of x. So what we do here? The derivative of, it's again f and f again. So this is f of x equal to some g of x into h of x. Right. We should not use the same name on either sides. So the derivative f dash of x is g of x into h dash of x plus h of x into g dash of x. So what's happening here is the derivative of the product g of x into h of x is g of x into h dash of x plus h of x into g dash of x, which means first function into the derivative of second function plus second function into the derivative of first function. That is the rule. First function into derivative of second function plus the second function into derivative of the first function. Okay, this is to be remembered. This is way more important than all other rules, and this will be having a wide application in our future calculations and all. So let's say an example. Let f of x equal to say 8x cube into 5x minus 2. 5x minus 2. F of x equal to 8x cube into 5x minus 2. Can you identify this as a product of two functions? See, 8x cube can be seen as a function and 5x minus 2 can be seen as another function. Right. So, the derivative f dash of x will be, how did we define it? First function into 8x cube into derivative of second function. Second function is 5x minus 2. So, it's a linear function, right? ax minus b or ax plus b. So the derivative of a linear function will be the coefficient of x. So the derivative is 5 here. Right. Plus second function into, what is second function? 5x minus 2 into the derivative of first function. What is the derivative of first function? 8 into 3 into x square. 8 into 3 is 24 into x squared. See, if I make any mistakes in the calculation, you may correct it yourself during your studies, and let me know about it soon. So this is 40x cube plus 24 into 5, 120, 120x cube minus 48 x squared. Right. So this will be 120, 160 x cube minus 48 x squared. So the derivative of the given product is 160 x cube minus 48 x squared. Okay. Similarly, we have a formula for the quotient of two functions, the derivative of quotient of two functions. Let's examine that as well. Quotient rule. Suppose we have a function f of x equal to some g of x by h of x. Remember, whenever we write a fraction, make sure that the denominator is non-zero. Okay, so this is given as g of x by h of x. Then the derivative f dash of x is defined as second function into, listen, the order is important here. In our previous expression for product rule, the order was not a problem. We could have written in any order. But here the order matters since we have a negative sign getting intruded. We'll see. Second function into, or not second function here, just call it numerator and denominator. So denominator into derivative of numerator minus numerator into derivative of denominator divided by the denominator whole square. How was it? The derivative of quotient g of x by h of x is denominator into derivative of numerator minus numerator into derivative of denominator divided by denominator whole squared. Denominator whole squared. Remember this formula. Be cautious that the order matters here. Right. See, a minus b and b minus a are not the same. So you cannot interchange the order here. You have to be very careful. It has to be in the same order. Right. Let's see an example. So let f of x equal to 2x raised to 4 divided by 5x minus 6. Then the derivative f dash x. We can identify this as a quotient where we have two functions. One is 2x raised to 4 and the other is 5x minus 6. So the derivative is given as denominator into, so 5x minus 6 into derivative of numerator 2x raised to 4, so 2 into 4 into x cube, which will be 8x cube, minus numerator into derivative of denominator, which is 5. Right, this is a linear function and the coefficient of x will be the derivative divided by 5x minus 6 whole squared. Okay, so what is this? I mean, if you want to, you can simplify this. Like this will be 40x raised to 4 minus 6 into 8, 48x cube minus 10x raised to 4 divided by 5x minus 6 whole square. Right. So 40x raised to 4 minus 10x raised to 4 will be 30x raised to 4. If you want, you can simplify it again if you want to. Right. So this is how we find the derivative of a quotient of two functions.